In this video, we're going to use the theory about non-inertial reference frames that we discussed in the last video to attack the problem of the tides. So the tides occur, of course, due to the influence of the moon or the sun on the Earth's oceans. This is roughly what it looks like. If the moon is facing the Earth like this, then the height of the oceans on the side that faces the moon is higher than on a side that's 90 degrees away from the moon. And we also have the same effect on the side that's opposite the moon. So high tide occurs both when the moon is in zenith or close to it, and in nadir or close to it. We will explain mathematically why we get it on both sides. Intuitively, you might want to think, intuitively, you can kind of understand why it should be on this side, but why you would have a movement of water away from the moon on the opposite side is perhaps a little bit less intuitive. So I have a question for you that we will discuss in class. Aside from the mathematical formulation that we are about to derive, can you come up with a physical explanation, not using any equations, just a physical explanation for why high tide occurs both on the face of the Earth that is facing the moon and the side that is facing away from the moon? Okay, so let's look at this in a little bit more systematic fashion. First, we will introduce a vector here that goes from the center of the moon to the center of the Earth. And we're going to call that vector d0. Okay. And we will also pick some parcel of water here on the ocean of mass m. And we're going to take another vector that goes from the center of the moon to that parcel of water, like that. And I'm going to call that vector d. Now what's going on here is that the Earth is accelerating towards the moon. If we take the mass of the Earth and multiply it by the Earth's acceleration, which I'm going to call a here, we know that that's going to be equal to gm little m divided by d0 squared, right? That's the distance between the moon and the Earth. And the acceleration is in the negative d0 hat direction. That is in the opposite direction than the d0 points. Let's use consistent notation here for the masses. So that's the mass of the Earth and the mass of the moon. Okay, so that gives us then that the acceleration is given by this. Next, we turn to the force on this parcel of water. So it experiences a force F, which has several courses, right? We will have, well, in principle, we have some non-gravitational force, F and G, due to interaction with neighboring parcels of water, pressure and other things. And then we have mg, which pulls it towards the center of the Earth. And then we have the gravitational pull from the moon. So that is going to be then minus gm moon times the mass of this parcel. It's going to be in the minus d hat direction, that's why I put the minus sign there, divided by d squared. So it's essentially the same form that we had over here, except that now instead of the mass of the Earth, we have the mass of the this little parcel. Now the Earth is, for our purposes here, a non-inertial reference frame. If it weren't, we wouldn't have any tides. So that's important to take into account. And then, just as we have just shown in the last video, we get that Newton's second law will now have a modified form where the mass of this water parcel times its acceleration equals the total force minus m times the acceleration here. And this is Earth's acceleration here. And we can then write all this out. And we get a plus sign here because of minus and minus. And we can then rewrite that, if you like, as like this. So we have mg, we have the non-gravitational forces, and we have what we're going to call the tidal force. The tidal force is minus m, minus g, m moon, mass of the water parcel, like that. Okay, so this is now the tidal force. So it is actually a combination of a real gravitational force, that's this part of it here, and an inertial force due to the fact that the Earth is accelerating towards the moon. So it is a hybrid force, if you will. That's a tidal force. So if we take a look at how that actually acts in the system that consists of the Earth and the moon, do that here. Make this a little bit larger. And colors are nice, but I'm going to take away the color from the inside. Okay, so let's see now. If d equals d naught, so let me just quickly generate them. We also should put in that this is going to be the radius of the Earth, RE, of course. Okay, so we can see now that if d equals d naught, then under those circumstances actually the tidal force is 0, so the tidal force is 0 at the center of the Earth. Not that the Earth is exactly centered here, but if we do it like that, it is. The center of the Earth, the tidal force is 0. Of course, there's no water there, so we're not too interested in that position. But if we move towards the moon now, then this term becomes larger, and we get a tidal force in the minus d hat direction, that is towards the moon. So we actually get a small force, tidal force in that direction, in this position. If we move away from the Earth, away from the moon, then the second force becomes larger than this one, since d now increases. And F tide is in the direction opposite the direction towards the moon. You get a positive sign here. It's in the d naught hat direction. And therefore we get some tidal force over here. If you're at this point, which is 90 degrees away from the moon, well, at that point, d squared and d naught, d and d naught are about the same size. So you get then a force that's acting in the direction of d naught minus d. So if I take d naught here, subtract d if it's pointing to this point, I will get a direction like so. In other words, the tidal force over here is pointing inward. And similarly over here. Okay, so those are the directions of the tidal forces. And that kind of explains why the tide looks like this. Okay. Now, our job, I didn't mention it, but our job here is actually to figure out the height of the tide, which you should be able to do here from what the forces are. So to find the height of the tide, we will make an assumption, which is partially true. assumption we're making is that the surface of the ocean is equipotential. In other words, if we can associate a potential energy with its total force that's acting on the water parcel here, then that's going to have a constant value across the surface of the entire ocean. This is true as long as there's no flow in the water. Because in that case, the non-gravitational forces that act on the water parcel are just the forces due to pressure. And the pressure is going to be perpendicular to the surface. That in turn gives us that mg plus F tide is perpendicular to the surface. And since the forces are the gradient of the potential, and therefore point in a direction perpendicular to the equipotential lines, this gives us that the surface of the ocean is equipotential. Essentially, if we have surface of an ocean here, water underneath, we know we're going to have, this is going to be F tide plus mg. It's perpendicular to the surface of the ocean. Since this can be written as minus the gradient of some potential, that potential has to have a constant value along the surface of the ocean. And that's going to be the assumption that we use. So our next task then is to find potentials that are associated with mg and with F. That is not so difficult. We know, of course, that if we can write mg as the gradient of some gravitational potential with a minus sign, that amounts to saying that u gravity equals mgy, where y is the direction out of the surface. Actually, I'm not going to use y. Let's use r instead, right? So things are, it's clear what we're meaning by r. It's the radial direction from the center of the Earth. For the tidal force, it's a little bit more complicated. We have to find now some potential that satisfies this. Okay, so I'm just going to give it to you. It will be minus gm moon times m times 1 over d plus x over d naught squared. Okay, so first of all, it's kind of easy to see here. D is like a radial variable. So the gradient of 1 over d is going to be d hat over d squared. Just take the derivative of this. D naught hat, on the other hand, is in the x direction. So if we replace d naught hat with x here in the potential, take the gradient of x, we get x hat. X hat is the same as d naught hat. And d naught itself is a constant, so it doesn't figure in any gradient. So these are the two potentials that we're working with. The gravitational potential and the potential that's associated with the tidal force. Okay. Now let's look at what's happening on the surface of the Earth here. I'm going to name these points here, the points that are facing directly towards and away from the Earth, from the moon, excuse me. I'm going to call P. And these 90-degree points here I'm going to call Q. Okay. And no matter where we are, we're going to have that the potential is the same everywhere. So the surface of the ocean is equipotential. Therefore, we can say that the potential at point P at the surface of the ocean is equal to the potential at point Q. And that's then taking that the potential here is U tide plus U gravity. So we can write it out explicitly here. We have that U gravity at P plus U tide at P equals U gravity at Q plus U tide at Q. And we'll rewrite that. Now this is the gravitational potential between high tide and low tide. So this is mgh tide. The height of the tide times mg, that's this differential in potential. So now all we have to do in order to calculate h tide is to find these two potentials at the point Q, where we have low tide, and at the point P, where we have high tide. Just to make that explicitly here. And low tide. I will need this figure, so I'm going to copy it and bring it with me too as we scroll down here. So you're operating at this point, or that point, and at this point. So what we really need in order to calculate U tide at the points Q and P are the value of D at those 2 points. Right. So at the point Q, D is going to be equal to the square root of D naught squared plus the radius of the Earth squared. Right, that's the distance from there to there. And at the point P, D is just D naught plus or minus the radius of the Earth. Okay, now let's grab this expression too. Okay, so those are the things we're working with. And now let's just do the calculation. And this 0 comes from picking the origin at the center of the Earth, which is convenient. Now the radius of the Earth is a large number, but it's going to be small compared to D naught. So we can do a little bit of a Taylor expansion here. So just to remind you of that, the square root of 1 plus x is approximately equal to 1 plus x over 2. Also, the square root of 1 plus minus x equals 1 minus plus x squared. I'm not going to use, and then there are higher order terms here too. This time I'm not going to use the x squared term. I'm just going to keep the 1 over x here. And what that tells us is that this is equal to the following, approximately. So that's U tide Now we just have to do the same thing for UP. Then I'm going to make use of this Taylor expansion here. And I'm now going to use both the term in x and the term in x squared, because this one, as you'll see, will disappear. There, disappears. All right, then we just have to use what we found up here. That MGH high tide is this difference here. MGH tide and these masses go away, as they should. It's just the mass of the parcel of water, and that obviously shouldn't affect the height of the tide. Now we're almost there. We just have to use an expression for G, and you should be able to show this yourself. And we then obtain our final result. So that's the height of the tide. Now, a few things we can tell from this. It is very sensitive to the size of the Earth. And the height of the tides goes to 0 if the Earth has 0 radius. And for a larger Earth, if we were to double the radius of the Earth, for instance, keeping the mass the same, we would have a tide that would be 32 times larger. Of course, the mass of the Earth would increase by the same amount to the cubed, so the tides really go as the radius of a planet, because the mass of the planet is proportional to the radius cubed. It's also sensitive to the distance to the moon through the third power. And the distance to the moon is relatively small. It would then seem that the tide from the sun shouldn't be so large. But since the sun weighs so much more than the moon, actually the two tides are kind of comparable. In fact, we get that if you plug in the numbers for the moon, the tide is going to be about 54 centimeters, while for the sun, it's on the order of 25 centimeters. Now, real tides can be both higher and lower. That's because of the assumption that we just made of no flow. In reality, of course, the tide also causes the water to flow, and then it can be funneled into bays, etc., which can make the actual tide in a given location much larger than these numbers. Now, because the tides from the sun and the tide from the moon are comparable, although the moon tide is clearly bigger, the height of the tide varies quite substantially by the moon cycles. There are two extreme cases. So if we take, this is the Earth here, then if the moon is here and the sun is there, then the two tides will add up, right? Because the high tide from both the moon and the sun are in the same position. It gives us H tide on the order of 79 centimeters. This is known as spring tide. And it occurs when we have either full moon or, as depicted here, new moon. And then the opposite, of course, is when the moon is half, like this. In that case, the tide is going to be the difference of these two. 29 centimeters, less than half of the high tide during spring tide. And this, let me make some more room here to make sure that it's clear that they're separate. And this is known as neap tide. And it occurs when the moon is half. Which is good to know. And we have been able to explain that quite clearly with this simple calculation. Okay, so that's as complicated as things are going to get when you're working with linear acceleration. Next, we're going to tackle rotational non-inertial reference frames, and things then get a little bit more complex, but the basic idea remains the same.